We saw some properties of the Bernoulli map in the Bernoulli shift last time. Let me introduce you to another map which is similar to the Bernoulli map, which has similar properties and is closely related to it, and is perhaps a little easier to understand because it is not a discontinuous map, and this is the so called tent map, which looks like this. It is given by the function xn plus 1 is twice xn, doubling map as before, provided 0 less than equal to s xn less than equal to half, and it is 2 minus 2xn for a half less than equal to xn less than equal to 1. It is again a map of the unit interval specified by this piecewise linear function, and we can draw this map very easily. So here we have xn and then xn plus 1, and it is 0 to 1 on both sides, and this goes up there and comes down here at a point half. The map changes slope from plus 2 to minus 2. Again it is an onto map of the interval, no point is left uncovered. It is not 1 to 1 because it is clear the map is not invertible. For every value of xn there is a unique xn plus 1, but the converse is not true. For every xn plus 1 there are two values of x sub n, and therefore if you give me a final point x sub n, there are 2 to the n possibilities for x0 from which this final point could have arisen. So it is not invertible and it leads to chaos for a very obvious reason, because the phase space is bounded. This is the bisector, there is a fixed point here at the point 2/3. So the coordinate of this is 2/3, as you can easily check, and it is unstable because the slope has magnitude 2 at this point. The fixed point at the origin is also unstable, again the slope is 2. What do the iterates of this map look like? Well, the first iterate of this map, if I plot x versus f2 of x, this would be something like slope 4 goes up and comes down, and now you have once again you have the fixed point of the map, and then you have a period 2 cycle between these 2 points, and then an unstable fixed point here as before. And as you take further and further iterates of this map, you have many more spikes up and down, and the slope at every one of those points is greater than 1 in magnitude, and therefore not only the fixed points of this map but also all the periodic orbits of this map are unstable periodic orbits. It is easy to check once again that the points which lie on periodic orbits are a set of measure 0, they are dense everywhere on the unit interval and they are a set of measure 0 once again, and the map is fully chaotic. It is completely chaotic in the sense that any typical initial condition from the set of irrational values of x would lead to an orbit that does not settle down to any final point, and it wanders uniformly over the entire interval. We still have to find out how ergodic is this system on the unit interval. It is an ergodic system, that is clear, because typical initial points sooner or later go to the neighborhood of every point on the interval. So by our earlier definition of ergodicity, this is an ergodic system. It is in fact a system which is exponentially unstable in the sense that it has a positive Lyapunov exponent in this case, and the Lyapunov exponent is again log 2. We will verify that, we will prove that rigorously in a little while, but it is exactly the same in magnitude and value as the Bernoulli shift. In fact, in physical terms, in the Bernoulli shift what we did was to take the unit interval 0 to 1, we stretched this interval by a factor of 2, so it really got doubled when you did 2xn, so it went from 0 to 2, and what did the Bernoulli shift amount to? It amounted to taking this part of it, cutting this if you like, and putting it right back on top of this. So you ended up with something that looked like this, just pictorially between 0 and 1. So this thing was snipped off here, cut and put back onto this in this fashion. and this is what led to the non-invertibility of the map, because you really have 2 pre-images for every point and then 4 pre-images if you go 2 iterates backwards and so on. This non-invertibility is what led to chaos, eventually led to the complicated properties of this map. So you must not get deceived by the piecewise linearity of the map, it is only piecewise linear, but it is a non-linear function all the same, because we saw that a linear map was very trivial, it had a single fixed point in general and that was it. On the other hand, a nonlinear map has these very strange properties, the fixed point is unstable in these conditions, all the periodic orbits are unstable, and the entire unit interval becomes the attractor, in this case a completely chaotic attractor, because A, the phase space is bounded, B, there is exponential sensitivity to initial conditions, and C, there is a dense set of unstable periodic orbit buried in this phase space. So all the conditions we laid down for the existence of chaos are met, and these are fully chaotic maps, both the Bernoulli shift as well as the tent map, completely chaotic maps. We could try to trace the origin of this chaotic behavior in the following way. We could say, well, instead of looking at this particular map, the tent map which becomes an onto map, suppose we did the following. Yeah, that's a question.
Because Bernoulli map is a chaotic map, this has to be a chaotic map, because just in one half of the region is just the image of.
Yeah, it is simply the same thing, because what he is pointing out is that in the Bernoulli map you started with this and then you, so to speak, stretched it like a rubber band, you stretched it all the way from 0 to 2, 1, and then you cut and put it on top in this fashion. This is what you did. So this portion was cut and placed on top, right on top of the unit interval between 0 and 1. In the tent map, on the other hand, you started with 0 to 1 and then you stretched it by a factor of 2 all the way, and then instead of cutting and pasting on top, you bent it for backwards. So in that sense what you did was to go here and then bend it backwards. So this was flipped over and bent backwards, and again you produce this 2 to 1 effect, and once again all the periodic orbits were unstable and so on. So you can do it in many ways in phase space, you do the stretching and then you cutting and pasting, cutting and putting it back, or you stretch it and bend it back in this fashion. So these are typical mechanisms by which chaotic attractors are produced. We will see some more examples of this in higher dimensions. So coming back to the tent map, suppose we look at it as a member of a whole family of maps of the following kind. So here is the map function, here is 0 to 1, there is the bisector, and suppose the map function is of this kind, it is a line with some slope r up to a half, and then it folds back to 1 on this side here, and let us write this map down. So we have xn plus 1, or f of x in this case, the map function is equal to, depends on what you would like to call r, so let us call this 2r x with slope 2r at the origin for x 0 less than equal to x less than equal to half, and what is the rest of this equal to? You would like it to vanish when x equal to 1, right? So it is 2r times 1 minus x for a half less than equal to x less than equal to 1, and it is continuous, because when x is equal to half it is just r, the maximum value is just r, and that is true here too. So this point here corresponds to r. The slope at the origin, which is the only fixed point in this case, is 2r. So when is this fixed point stable? When 2r is less than 1. So the fixed point at x equal to 0 is stable for 2r less than 1. or r less than a half. What happens at r equal to a half? At r equal to a half, exactly equal to a half, it is evident that this map goes right up to half and comes back in this fashion. So it falls on the bisector and then comes back here. So this corresponds to r less than a half, this map corresponds to r equal to a half, and where are the fixed points of the map at r equal to a half? Everywhere, everywhere. This map is degenerate, everywhere, all these points remain exactly where they are. What if I started with a trial value greater than a half for this map at r equal to a half? What would happen? Well, I'd start here by this staircase construction, and in the next step I'd go here, and that's the end, I stay there. So it's clear that this map is degenerate. The entire set of points from 0 to half is a fixed point, so to speak. Now what happens as soon as r exceeds a half? Well, here's a typical value, r exceeds greater than a half, and it looks like this. So in this map, half is less than r is less than 1. Remember, the peak is at r. And what sort of fixed points do you have now? You have a fixed point here, but you have another fixed point there, and the slope in each of these cases is 2r in magnitude, and that is greater than 1. Therefore these are unstable fixed points definitely, and it is easy to see that the iterates of this map would all lead to unstable fixed points, and therefore all periodic orbits are also unstable immediately. And what happens at r equal to 1? It becomes the original tent map. It is called the symmetric tent map at fully developed chaos, because we will see why it is fully developed chaos in a second. So this is the map for r equal to 1. This is the original tent map, and the entire unit interval is now covered. It is an onto map, and you have a chaotic attractor which runs all the way from 0 to 1. But now let us try to draw a bifurcation diagram for this, for all the equilibrium points in x as a function of the parameter r. So if you did that, so let us call these fixed points, let me just call them equilibrium points just to have our idea straight, as a function of r. Here is 0 and here is r equal to 1. What would this figure look like? Till r is less than, as long as r is less than a half, there is only one fixed point, and that is at 0, and it is a stable fixed point. So by our normal ways of drawing the bifurcation diagram, this is stable here, nothing else happens. What happens as soon as r exceeds a half? Well, at r equal to half, it is clear this entire set of points, if you like, is fixed points. It is a degenerate map. And notice, if r takes on a value between 0, half and 1, there is no way you are going to reach any values greater than r, because the function never takes you beyond the point r itself. So the unit interval is not covered. Wherever you start, eventually you are going to fall into a window between 0 and r, and in fact what you do is fall into a window, and at r equal to 1 the entire unit interval is an attractor, it is a chaotic attractor. But in between till a half, this is 1, in between, after this there are no stable fixed points, there are no stable periodic points either. The system starts becoming chaotic, and the region into which the iterates fall gradually expands till eventually it sort of falls into the unit interval here. But what happens here is very, very interesting. A little band emerges, numerically one can explore this, and the system falls into this region here. There is a little window in x which is never covered asymptotically, you never reach that eventually. So the attractor is in two bands, there is a band here and there is a band here, and beyond a certain value of r which you can discover numerically, these two bands merge once again, and the entire interval here, this is a single band which continuous goes on all the way till this point, and in between you do not have any periodic cycles of any kind which are stable at all. We will explore this numerically. I will bring a figure which or demonstrate this on a computer, which will show you how this attractor gets built up. So chaos actually starts beyond a half, but it is not fully developed chaos, because you do not have complete, the entire interval is not part of the chaotic attractor. This portion and this portion, those values of x alone correspond to the attractor, and as you go along that gets bigger and bigger till eventually there is one continuous set all the way till 1. These curves are not as smooth as I have indicated here. It turns out this curve is a fractal curve in itself. One of these is a fractal curve, and there is a fair amount of intricate numerical complexity that goes on here, even though the map looks extremely simple. So even in this extremely simple map, this bifurcation diagram is fairly intricate. We are going to see many more complicated examples, but this itself already tells you that very simple one dimensional dynamics, all you are doing is a piecewise linear map of this kind. In graphical terms, all you are doing is to iterate this function over and over again for r greater than a half, and you end up with this very intricate kind of dynamics automatically. What do you think is the Lyapunov exponent for this map? We saw it is log 2 when r was equal to 1, but what is the Lyapunov exponent for this map for an arbitrary value of r? Exactly, it is just 2r, because the slope is uniform everywhere, and in these one dimensional maps, remember that this quantity f prime of x modulus is the local stretch factor. It is the Jacobian of a transformation, as you can see. If you change from x to f of x, this is in fact the Jacobian of the transformation. You take its modulus and you take the log of this gives you the local stretch factor, the local Lyapunov exponent if you like. And of course once you have a constant piecewise linear map with a constant value of mod f prime of x everywhere, that is the Lyapunov exponent for the map. We are going to shortly come across a map where this is not a uniform, it is not piecewise linear, there is curvature in the problem, and then this will not any longer be true, but right now we see that this is in fact the Lyapunov exponent everywhere. So let me write that down for this, pardon me, the log, yes, the Lyapunov exponent is log. So my statement was mod f prime of x gives you the local stretch factor and its logarithm gives you the Lyapunov exponent. So this map has lambda, the Lyapunov exponent lambda equal to log 2r. What happens if r is less than a half? If r is less than a half, you have this figure. Yes, the Lyapunov exponent is in fact negative. What does that suggest to you? That is going towards, the entire phase space is shrinking towards a fixed point. So even that works out, as you can check. And when does chaos happen? When does chaos start off? At what's the onset of chaos in this problem? At exactly a half. Slightly infinitesimally to the right of a half, you have a positive Lyapunov exponent, because log 2r when r becomes greater than half becomes a log of a number greater than 1 and becomes positive. So chaos is characterized by a positive Lyapunov exponent. That is what I meant by exponential sensitivity to initial conditions. If the largest Lyapunov exponent in a system happens to be 0, you have no chaos in this problem. There has to be at least one positive Lyapunov exponent. Now we talked about one dimensional phase space, x is a single scalar variable, so there is only one Lyapunov exponent, but in a d dimensional phase space or an n dimensional phase space there are n directions, and therefore in principle you could have n Lyapunov exponents, but you need to have at least one of them positive in order to have chaotic behavior. You could have more than one positive, and this can happen even in cases where the phase space is bounded, even in cases where the volumes are preserved, because there could be some directions in which you have stretch and some directions in which you have contraction, and as long as you have a direction in which you have a stretch, you have chaotic behavior under these conditions I have specified. You could even have a system in which there is an attractor and you could have chaos, in the sense that you could have a 3-dimensional system in which the attractor falls into maybe a 2-dimensional manifold or even some fractal manifold, dimensionality less than 3, but there could always be a stretching direction. So in sort of heuristic terms, think of it in this fashion: if I start with points which are kind of close together in a circle like this, and suppose this phase space area shrinks to a line, but suppose it shrinks in this fashion and it becomes a line finally. So in this direction things have shrunk, they have gone to a line, but in this direction they have expanded to system size in this fashion, and therefore initially neighboring points could have expanded arbitrarily far to system size itself. That itself implies loss of information and possible chaotic behavior. So this is typically what happens, even though the phase space is bounded, even though the whole thing is compact, even though the system could be dissipative so that phase space volumes actually shrink with time, there could still be chaos in the problem, because you still lose information. Initially arbitrarily close points could diverge exponentially fast with a positive Lyapunov exponent, at least one positive Lyapunov exponent, and that is sufficient to produce chaos. So in this figure, in this particular map, we see that the system proceeds very rapidly to chaos. It goes straight away from a stable fixed point to some kind of degenerate map and followed by chaos at once, no periodic orbits. This is not very generic, this happened because of the particular shape of this map that we happen to take. We can take other maps where this won't happen, and you might expect a slightly more gradual approach to chaos, and there are several routes to chaos in dissipative systems. Is this system dissipative or conservative? How would you classify this? What would you say? I would classify it as a dissipative system. We'll come back to this and I will point out why this is really a dissipative system in that sense, in a certain specific sense. We look at conservative systems, conservative maps which still have chaotic behavior.
If a map has a chaotic behavior,
yeah,
that means within the d lambda,
yeah,
dx, it can go to arbitrarily far apart.
As far as the system itself.
Yeah, then it has to be dissipative.
It has to be dissipative, absolutely. This kind of thing has to be dissipative. But we will look at a map, an artificial map no doubt. We will look at an example of a slightly higher dimensional Bernoulli shift in which you do not have dissipation, in the sense that the map is invertible, the area is preserved, and yet you have chaotic behavior. So we will get back to this. Okay. So now the next thing I want to do is take another prototypical map where things become a little more complicated, and this has to do with the logistic map. This was one of the first maps, in fact perhaps the first map where many of these features were elucidated to start with. It is a very simple looking map, but at the same time it can become very intricate indeed. Let me show you what happens here. This map is parabolic, it is just a parabola, and it looks like this. So the map function is given by xn plus 1 is equal to xn times 1 minus xn multiplied by a certain constant here, and we have many names for this constant. Let me call it mu. Mu is a real number, a positive number, and where are the fixed points of this map? Well, 0 is obviously a fixed point, and there is perhaps one more fixed point. We have to draw this thing here, so let us look at it. 1 is not a fixed point. 1 minus 1 over mu is a fixed point, clearly. 1 is not, because at 1 this vanishes but this side does not. So the map looks like this. In fact, we should draw the full map and then we will see why I am going to restrict myself to the unit interval. So let us put x here and f of x, which is mu times x times 1 minus x. Mu is positive. The map vanishes, this quantity vanishes at both 0 and as well as 1. So here is 1 and this map perhaps looks like this. It is a parabola, it goes up and comes down in this fashion. The largest value is at a half. That is obvious because x times 1 minus x has the maximum value at a half. Okay. Now I start with mu, a small positive number, and if this is the 45-degree line here, it is evident that this is a fixed point and it is stable because the slope near the origin is just mu, and as long as mu is less than 1, this slope, this fixed point is stable. Every point is going to get attracted to it. By the way, this map, it goes off like this and then quadratically, so it is quite clear that it is going to intersect at some other point here, and this fixed point is going to be unstable, and this is the figure for mu less than 1. We are not really going to be interested in points outside this unit interval, because if you start with some point here, it is going to get flow into this, and if you start with points out here beyond this fixed point, they are actually going to disappear to infinity, and similarly on the other side things are going to escape to infinity. What happens when mu becomes equal to 1? At mu exactly equal to 1, this fixed point becomes tangential in this fashion. I have drawn this badly. This value is actually 1/4 because that is the maximum value of x times 1 minus x between 0 and a half. So it is not drawn to scale, but this fixed point becomes marginally stable at mu equal to 1. What happens beyond mu equal to 1? It crosses. So let us draw that separately, and now let us start focusing on points in the unit interval. So here we are, 0 to 1, that is the bisector, and I am plotting f of x versus x, and f of x is mu x times 1 minus x. So originally for mu less than 1 I had something like this perhaps. At mu equal to 1 I have this. This is a marginal fixed point, and it is immediately clear that as soon as mu exceeds 1 it does this. The slope here has exceeded 1, but the slope at this fixed point is less than 1, so it becomes stable, and this fixed point at 1 minus 1 over mu, that becomes stable. We can easily compute what the value of that slope at that point is. And what is the value of the slope at this point? Let us compute that. So f prime of x is equal to mu minus 2 mu x. Okay. So what is the value of the slope at this fixed point? The slope at the origin is mu, of course, as we know very well. What is the value at that point? It is 2 minus mu. So it is evident that the fixed point at mu equal to 0 is stable for mu less than 1. At mu equal to 1 it becomes unstable, and a new fixed point gets in, which is given by this as soon as mu exceeds 1. For mu less than 1, remember this fellow was on the negative side. As soon as mu exceeds 1, you get a new fixed point in this unit interval, and its slope the fixed point at x equal to 0 at x equal to 1 minus 1 over mu f prime at this point 1 minus 1 over mu is equal to 2 minus mu. So the mod of this is this guy. So where is this thing stable? Till what value of mu is this stable? Till 3, because we want the mod of this. So from mu equal to 1 to mu equal to 3, this fixed point is stable, right. At mu equal to 3, this map is out here till 3/4. So you have this, and the slope here becomes equal to 1 at mu equal to 3. In fact, we can start writing down the Lyapunov exponents now, because if you have a stable fixed point, then the Lyapunov exponent is simply the log of mod f prime at that fixed point, because if you wait long enough, the iterates, all the iterates fall into this point, and therefore if you look at the definition of the Lyapunov exponent, which remember was equal to lambda by definition was equal to limit n tends to infinity 1 over n summation j equal to 0 to n minus 1 log mod f prime of the iterates xj. And now it is clear that if there is a fixed point, then all these logs are going to, this xj is going to be dominated by the value at the fixed point, and that is going to come out, and that is going to divide this n is going to divide that and give you that as the fixed, as the Lyapunov exponent itself. So the Lyapunov exponent is log mu as long as mu is less than 1. Between 1 and 3, the Lyapunov exponent is log mod 2 minus mu, and it is again negative, showing that there is a stable fixed point. So let us write this down, lambda for the logistic map equal to log mu for mu less than 1, 0 less than mu less than 1, less than 1, it is equal to log mod 2 minus mu again for 1 less than mu is less than 3. So you can see what is going to happen when mu becomes equal to 1, then this Lyapunov exponent vanishes, and you would think the fixed point has become unstable, and therefore the system is going to go chaotic like the earlier tent map, but that does not happen. This fixed point takes over and its log is less than 1 here, and therefore you again have stability. And now let us draw the bifurcation diagram and see what happens. So I need a long graph here in mu, eventually I will run out of space, but here is 0 till 1, which is not very interesting. Mu itself is the fixed point is at 0, and it has got a Lyapunov exponent which is negative. So you have this as a function of x equilibrium. Okay. And then this fixed point becomes unstable, so you should draw the bifurcation diagram with a dotted line here, and you have the other fixed point which is at 1 minus 1 over mu, which turned out to have negative values at mu equal to 1, it is 0, it crosses this and then takes over from here, and this fellow becomes unstable. Earlier that was unstable. What kind of bifurcation do we had at mu equal to 1? Exchange of stability bifurcation, right, and then you have a fixed point which goes along, and this goes along till you hit the value 3. At 3, this guy here becomes 0, and you would expect, okay, maybe now we are going to have a chaotic behavior. But what happens at 3 is that the map looks like this, but what does the iterate of this map look like? What would the first iterate look like? If you iterate this map here at mu equal to 3, I am not going to be able to draw it too accurately, but it starts looking like this. Okay, and let us draw it a little better than this. Starts looking like this, and you have this behavior here. This was the fixed point at 1 minus 1 over mu. But then you have two other fixed points for the iterate. This is f2. The fixed point at the origin continues unstable, of course, and this fixed point also becomes unstable mu equal to 3, but then you have this and that, and that is what sort of point is the orbit is that? It is a period 2 cycle, it is a period 2 cycle. So the system bifurcates to a stable period 2 cycle, which you discover by solving the equation f of x equal to x, and this is a fourth order equation because f of x is quadratic and therefore f of x is a quartic, and you have a fourth order equation, but you can solve it easily because x equal to 0 is a root which you do not want, which corresponds to this, and x equal to 1 minus 1 over mu is this root and you do not want that. So factor out x times x minus 1 plus 1 over mu, and the rest is a quadratic which will tell you what these two roots are. Simple exercise, and these 2 points form a period 2 cycle which is stable, and the system falls into that or into this, flip flop between these two. Okay. So the bifurcation diagram now has a new kind of bifurcation. This becomes unstable, but then it bifurcates into a period 2 cycle. This is not a pitchfork bifurcation. Looks like a pitchfork, but it is not. Remember, in a pitchfork bifurcation, a stable fixed point became unstable and created a pair of stable fixed points or critical points. Here a stable fixed point bifurcated by exchange of stability to another stable fixed point, and now it bifurcates into an unstable fixed point and a stable period 2 orbit cycle. So this guy here, this and this, is a stable period 2 cycle, and the system asymptotically flips between this value and that, okay. And this kind of thing is called a flip bifurcation. So at mu equal to 3 you have a flip or a period doubling bifurcation because the period has doubled. What would the lambda be here? Suppose these 2 points, which are some functions of mu, let me call this alpha of mu and this point here beta of mu, the functions of mu of course. What would the Lyapunov exponent be in this region? It would start at 0, but then it would become negative because you have now found a period 2 cycle which is stable. And what happens to the Lyapunov exponent by this definition? You have 2 values here in this summation, is not it? So what would the Lyapunov exponent be in this case? So it would just be log modulus f prime of alpha f prime of beta. It would just be that, right? Pardon me? It is gone because eventually, wait long enough, this thing becomes a constant at this value, it is a period 2 cycle, and then the n here divides this, and the limit it would just be this product of logs. Now that is less than 1, so it is stable. The mod of this product is less than 1 because the period 2 cycle is stable. and once again the Lyapunov exponent drops to negative values. And this happens for 3 less than equal to mu less than equal to 1 plus root 6. And that is easy to verify. All you have to do is to find out when this number here hits 1, and it hits 1 at root 1 plus root 6 here. So that happens somewhere here. This is no longer to scale, this is 1 plus root 6. Then matters begin to happen very fast as you change mu. At this point this period 2 cycle becomes unstable and you have a period 4 cycle coming out. That becomes stable. So it is not this iterate, but you have the iterate with a period 4 cycle as well as these points, and these are unstable now, so that becomes stable. So this is a period 4 cycle, a little more change in mu and it becomes a period 8 cycle. So the next bifurcation happens here, and this period doubling cascade of bifurcations starts happening. So you have a cascade as mu increases, and it happens for smaller and smaller intervals in mu. So eventually what happens is that you have a 2 to the n period cycle where n becomes unbounded, and that happens at a finite value of mu. This is called mu infinity and it is equal to 0.566 etc. or 3.566. This is known to 15 decimal places for this map. One can compute the value of mu infinity numerically. There are lots of scaling properties that happen here which I will not go into right now, but you have the end of the period doubling bifurcation cycle, this one at any rate, etc. So you have a whole lot of points which form part of this attractor, not a full interval, it is not a continuous interval at all. The limit points of all these period 2 to the n cycle out here is a set of points which has got a fractal dimensionality between 0 and 1, it is of the order of 0.57 or something like that. So it is a dust, it is a set of particles, a set of points on the unit interval. Yeah, I will come back and explain what fractals are, so when I do that remind me to go back and tell you this. It is not a continuous interval. At that point the Lyapunov exponent again hits the value 0, and then after that it has nowhere to go, it is actually exhausted. Stable fixed point, period 2 cycle, period 4 cycle, period 8 cycle, etc. All these are exhausted and the system becomes chaotic. You might ask, it never went through period 6, it never went through period 9 and so on. It went through period 1, 2, 2 squared, 2 cubed, 2 to the power 4 and so on up to 2 to the power infinity. So it still has surprises in store. At this point the system becomes chaotic, and after that you have a whole band in which the system rests, exactly as in the case of the tent map beyond r equal to 1, but it is not the full interval as yet. However, in this case the system has further surprises in store, and now let us draw the Lyapunov exponent and see what happens. So I plot as a function of mu, I plot the Lyapunov exponent lambda. There is no chaos as long as mu is less than 1, there is a fixed point here and it is some negative value, it is at log mu, and as mu equal to 0 of course it is at minus infinity, but then it comes up and does something like this, it is negative. At mu equal to 1 it is hitting the value 0, but then it starts becoming negative once again because it is now given by log mod 2 minus mu. and this goes on till the point 3 where again it hits 0, and incidentally in between 1 and 3 at mu equal to 2 something interesting happens. Let us draw the map for mu equal to 2. So I would like to draw mu equal to 2, the map function f of x is twice x into 1 minus x, and the fixed point is at a half because it is at 1 minus 1 over mu, and what is the slope at that point? It is 2 minus mu, right. So the slope is 0 and the log of that is minus infinity. So what has happened is that exactly at mu equal to 2 the map looks like this, and the slope here is 0. Remember that the stability of a fixed point was determined by the modulus of the slope at that point. If that slope was less than 1 in magnitude, then we said it was stable, and if it was greater than 1 it was unstable, equal to 1 it was marginally stable, but at mu equal to 2 the slope here is 0, and that is the least value the mod of this slope can take, and it is evident wherever you start that in this case how would you get to this point? I mean it is quite clear that this is the smallest magnitude you could possibly have, and in fact the map becomes super stable at that point. This fixed point becomes super stable. The log of that plummets to minus infinity, so this goes off to minus infinity, and that is because at mu equal to 2 the fixed point is super stable. So the Lyapunov exponent goes all the way to minus infinity. Pardon me? The significance is that it is the best stability you can have, can't have anything beyond that, because in this map if I start with any point here, I hit this and then I hit this, the approach to this is extremely rapid out here because it does not really wander around at all. Okay.
Does it matter even the 10th map at r is equal to half?
That was simply degenerate. That was simply degenerate. Yeah, that was simply degenerate. I mean the entire map function lay on the bisector itself, so nothing moved in that case. Yeah, I agree, that is a sort of a degenerate case which is very unusual, but here when the slope is, no I am not saying this is more stable or less stable, I am simply saying it is a matter of terminology that when the slope becomes 0 then the map is, the fixed point is said to be super stable. It is stable if the slope is less than 1 in magnitude, and when it is 0 which is the least value it is super stable. The significance is that the corresponding Lyapunov exponent goes to minus infinity, tends to minus infinity. Okay. So the local stretch factor or contraction factor is the biggest it can have.
But my question is,
yeah,
if lambda were to be an indicator of the stability,
yes,
then this fails, right? My lambda in the 10th map.
I am not saying lambda is an indicator of stability, I am saying lambda if it is positive is an indicator of instability, but when you have isolated fixed points then lambda tells you in some sense what the contraction rate is, and the contraction rate here is the largest, and that is because it is directly measured by the log of this modulus of this slope here. Okay. There is another measure which says more precisely how contraction occurs in phase space as you move forwards in time, or expansion occurs as you move backwards in time, and that is measured by something called the Kolmogorov entropy. I have not introduced that as yet, and when the system is super stable then the Kolmogorov entropy also behaves, has a very specific kind of behavior. That is the reason I called it super stable at the moment, but for the moment let us leave this as just a matter of terminology, we will come back and see what it signifies. But it is easy to see that in this case the Lyapunov exponent will actually go to minus infinity here, then it comes back, crosses this at 3, and then because now at this point a period 2 cycle takes over, it falls back once again, and then there could be possibilities that these the periodic cycles themselves become super stable if any one of them, if the point half, if this point becomes a fixed point or part of a periodic cycle, then you can see immediately since the slope there is 0, if the peak becomes always, any of the peaks becomes, or the extrema of this map or its iterates becomes part of a periodic cycle, you have super stability there immediately. So this could happen over and over again, and then again at the point 1 plus root 6 it climbs up to 0, but once again a period 4 cycle takes over and it keeps doing this till it hits mu infinity. At mu infinity it's exhausted this and the Lyapunov exponent crosses over finally to positive values and the system becomes chaotic. So this here is the start of this chaos here. At mu equal to 4, that is the largest you can have here. So let us jump straight to mu equal to 4, which is here. So the maximum occurs exactly at 1, it becomes an onto map, then it displays properties very similar to that of the tent map, because now at this stage you have 0 to 1 and 0 to 1 here, this fixed point is at 3/4 and it is unstable. All the iterates of the map also lead to unstable fixed points, there are no more stable periodic cycles possible and this map becomes fully chaotic and the entire unit interval becomes part of, so at mu equal to 4 the entire unit interval becomes part of the attractor. But in between this end of this first period doubling cycle to the reaching of this chaotic attractor, you have many intricate phenomena that go on here between mu infinity and 4, because what happens is although all the 2 to the n period cycles became unstable, there are many other integers and we have not exhausted them. So it turns out that this map exhibits cycles of all integer periods 1, 2, 3, 4, 5 etc., etc. Not necessarily all of them stable, but eventually what happens is various complicated things happen here which we will describe by and by, including a phenomenon called intermittency. So there are long regular bursts of the iterates followed by chaotic intervals followed by regular bursts and so on, and eventually at the point 1 plus root 8 a period 3 window takes over. So for a little bit of time there is a period 3 cycle, and the period 3 cycle happens at 1 plus square root of 8, which is still less than 4. A set of tangent bifurcations occurs. So you have a stable fixed point and unstable, a stable, unstable, a stable, unstable, and the system flips between these, and that remains stable for a little while. So you have a stable period 3 window, the chaos disappears, and then once that disappears, that periodic window disappears, again chaos takes over and you have a chaotic behavior here finally, till at mu equal to 4 you have what is called fully developed chaos. And we will have more to say about this. Okay. And the question is, what is the Lyapunov exponent at mu equal to 4 when the entire unit interval is completely chaotic? It turns out that the Lyapunov exponent is, can you guess what it would be? Because it now has properties very similar to the tent map in some sense. It is log 2, it again becomes log 2, even though in this case the slope is not uniform. So you really have a complicated behavior, the system is ergodic on the unit interval and ends up with a limiting value of the Lyapunov exponent which is log 2 once again. And that stage, so it hits something here, a limiting value at mu equal to 4, this value is log 2. In between in this chaotic region the Lyapunov exponent has only to be found numerically, there are very few analytic expressions. What would be the value of the Lyapunov exponent in this periodic window? It would become negative in general. If there is a stable periodic window it would simply become negative. So it is not as if this stays and goes up monotonically to log 2, there are still complications here, it still goes up and down and eventually hits the value log 2. Yeah, this is a numerical result here as to where the period 3 window emerges. So the statement I made was, after the 2 to the n cycles ended, after that set of period doubling bifurcations, you had the onset of chaos at this point. Exactly at mu infinity the Lyapunov exponent is 0, and right above for any infinitesimal value of mu beyond mu infinity, for an infinitesimally larger value you have a positive Lyapunov exponent. The system becomes chaotic, but in between, in this chaotic region, it is interspersed with periodic motion, and the last of these, the very last of these periodic windows happens at 1 plus root 8 as a value of mu, when the chaotic attractor disappears and the system falls into a stable period 3 cycle. So there are 3 points and it flips flops between these 3 points. That continues for a while, a small range of mu, and eventually that periodic cycle becomes unstable, all the other integer periods also become unstable, and the system has no recourse but to become fully chaotic, and this continues till mu equal to 4. Okay.
So what is the origin of the 3 period cycle?
Okay, now the question is, where does this come from, because we only looked at the iterates of this map, we did not ask what are the other possible periodic points. It turns out that in this map, for good reasons, the route to chaos is via period doubling. So you start with period 1, and that is double to 2, that is double to 4, which is double to 8, and so on, but this is only one set of possible periodic orbits. You could still have period 3, 5, 7 or any other number which is not of the form 2 to the n. All those periodic orbits appear in this region. Most of them are unstable when they appear, but occasionally you could have stability once again, simply because of the dynamics, which is not trivial at all, it is extremely complicated. And finally the last window that appears where you have a stable periodic orbit is a period 3 window right here, and once that too becomes unstable you have full chaos, complete chaos. The attractor at this point is not an interval, it is called the Feigenbaum attractor at mu infinity. Lambda is just about to cross over from 0, and the attractor is called a Feigenbaum it is not chaotic because chaos has not set in yet, the lambda is still equal to 0, it is not taken off to positive values. This is the limit set of this set of bifurcation points, and that is a fractal object, it is a set of points with a certain dimensionality called a fractal dimensionality, which is between 0 and 1, and it is non-chaotic. And because it is not an interval but a set of points which has a certain structure, it is called a strange attractor, but it is a strange non-chaotic attractor. I earlier introduced the idea of strange attractors in 3-dimensional or higher dimensional flows which were chaotic with at least a positive one positive Lyapunov exponent, but here is a case where the Lyapunov exponent is dead 0, and yet you have an attractor which is not a periodic attractor of any or anything like that, but it is a strange non-chaotic attractor at this stage, but immediately after that you end up with a chaotic attractor. Okay. Now we will come back to some of these points. In particular we want to study this, we want to study fully developed chaos and see what happens at this point, but first one quick question, what happens if I have a map in which mu becomes greater than 4, what would that look like? Well, it is evident that this would go like this. Then if you took this map seriously, what would happen? It is quite clear that what could happen is the following, remember this graph goes on both sides. So if I start with a point here, it goes here, I go there, and I am out of the unit interval and it leaves the unit interval. Till mu equal to 4, points which started inside the unit interval remained inside there, but now things have started escaping out of it. All points do not escape, all the pre-images of this interval would escape, the pre-images of this interval would escape, and so on. So you have a very complicated set of points which would escape and another set of complementary set of points which would remain inside, and these would form what are called Cantor sets. So we will talk about this in the context of the tent map. So what you have here is something called a chaotic repeller, because things are moving out of this interval, they are getting out here, and this too has its uses. But when you are studying chaos, it is up to 4 that you would like to look at. Yeah.
If certain points get
yeah.
away from the unit interval,
yeah.
then it's not going to be densely bounded between the 0 to 1 interval, right?
But what's going to be, the question is, if points leave the interval,
yeah,
then
those points will are not going to be densely moving across the 0 to 1 interval, right?
Exactly. So now what will happen once things, he's got a point, he says if you have a situation like this and some sets of points leave the interval, then what remains as an attractor is no longer the unit interval, and that is absolutely true. So what remains here is what I would call a Cantor set, and we will talk about this.
Would you still call the situation as chaotic?
It is still chaotic because there still could be exponential sensitivity to initial conditions between what remains, that could still happen, does not matter, No, but if I start with a point in whatever is left as an attractor, you still have a Lyapunov exponent, you still have unstable periodic orbits, you have all those points, a certain set of points has left. So your attractor, instead of being the unit interval, has split up into many disjoint pieces.
So as mu increases further,
yeah,
your set of points which are going to hover within this region is going to reduce.
Yes.
So it again moves towards stability.
Yeah, in some trivial sense. I mean, once I get out up there, everything has gone off to infinity. It is no longer stability, everything has just moved off to infinity.
It is not chaotic either.
It could be chaotic. While it is doing that, it could certainly be chaotic. Whatever is left inside. Okay. Whatever is left inside. And
that thing which is going to be left inside is going to reduce. So can you say that
things have now become unbounded, right? This motion is now going off to infinity. So I understand that fully, completely. Things are just escaping to infinity. That is no longer of direct interest. What is of interest is the following, which is to say that it does not really go off to infinity is to take this map and put this not on a square but on a square lattice, repeat this map over and over again. So I say when something goes out, it goes into the next square, and that is how I study scattering, and it is in fact a model for studying chaotic scattering for real physical systems, again as a toy model. Okay. So we will get back to this the next time.